Welcome you all. In this session, we'll move ahead. We are discussing about nozzle and we have discussed different parameters on nozzle. Right? Now, in this section, we will discuss about frictional loss in nozzle. Right? Because nozzle, we already know that nozzle is a device in which velocity is increased several times at an expense of pressure. Okay, and due to some friction, there are different types of losses, right? So we need to calculate this friction loss. Because whenever the steam glides over the surface of nozzle, due to the skin friction, there is loss in enthalpy. Because in ideal condition, we have assumed that the expansion is reversible adiabatic, like isentropy. But in actual practice, this condition does not happen due to some losses. So instead of expansion in nozzle as we assumed as isentropic process, the nozzle, there are some losses in nozzle. Okay, so we need to understand this one, right? So let us suppose the nozzle enters into entry point. This is the entry point of nozzle, right? Let us suppose this is nozzle. Okay, right? This is entry point. This is exit point, right? So this is the entry point. Okay, and when the nozzle enters into when the air enters into nozzle, we are assuming that the expansion is isentropic. Okay, so that's why this line will be vertical. This is TS plot. Okay, on TS plot, this line will be vertical because when this this expansion, if we assume that this expansion is isentropic, if expansion is assumed isentropic, that means enthalpy will remain constant. So enthalpy at point 1 is equal to enthalpy at point 2. But due to some losses, this nozzle expands like that. It follows the path 1 to 2s. Okay, this is for ideal condition. This is the ideal condition. But in actual condition, instead of 2, okay, this is 1, this is 2s, right? This is the actual expansion in nozzle. This is 2s, right? So now we have to assume that how much losses is there. Okay, due to some losses, this is actual expansion, right? So in this case of ideal condition, the enthalpy drop, how much enthalpy drop? This H1 minus H2 in this condition, this enthalpy drop will be H1 minus H2, right? This is enthalpy drop this is del H ideal. This is del H ideal. When it is assumed that the expansion is isentropic, in this condition, enthalpy drop in nozzle due to expansion, this is called del H ideal. Okay, but in actual condition, the nozzle expands Okay, this process is not isentropic, or and in this condition, this del H actually is equal to H1 minus H2S. Okay, so now in this condition, we can find out the nozzle efficiency. In this condition, we can find out okay. In this condition, we can find out nozzle efficiency. Okay, so this H1 minus H2, H1 minus H2, this H1 minus H2. This is del H ideal, H1 minus H2S, del H actual. So in this condition, the efficiency of nozzle this is equal to del H actual by del H ideal. And del H actual is H1 minus H2S, and this del H ideal is equal to H1 minus H2. This term is called nozzle efficiency. Nozzle efficiency, right? And the friction loss is because the actual enthalpy drop is H1 minus H2S. This is del H actual. When it is assumed that this process is not isentropic, okay, this is the process, okay, but in ideal condition it is assumed that the process is isentropic. So what is the losses? What is the loss due to friction? This is friction loss. The friction loss is equal to del H ideal minus del H actual. Okay, del H ideal is this. Del H ideal is H1 minus H2, and del H actual is H1 minus H2S. Right? This is called friction loss inside the nozzle valve. This situation is plotted on HS plot. Okay, right. Okay. We have to prove that C is equal to gamma height. This equation has been asked several times in examination. If dP by d rho is equal to C square, then prove that C is equal to a square root of gamma height, where C is the velocity of sound wave. Right? This is okay. This is very simple. For isentropic flow, we know that this PV gamma is equal to constant. This is very general communication. In terms of density, we can write, because density is equal to 1 by specific volume. This is specific volume, right? Okay. Because specific volume is equal to volume per mass, and density is equal to mass of volume. Okay. So it can be written in terms of density. This, okay. That means P into rho power minus gamma. This is constant. Okay. Just take a numerator. Now we have to differentiate partial. We have to differentiate partial distribution. Okay. After differentiating, we will get P into, this is minus gamma, gamma minus 1 into d gamma. And this is gamma raised to minus, and this is dP. Okay. If we arrange this one, we get this dP by d gamma. dP by d gamma is equal to gamma p by rho. This del p by, or you can say that okay, del p by del rho is equal to gamma p by rho. Okay. Just we have to simply differentiate this distribution partial. Okay, you will get this one. We know this dP by d rho is equal to C square. This is given in condition. That this implies C square is equal to gamma p by rho, and from where C is equal to square root of gamma p by rho. We know PV is equal to MRT Okay, this P, right. The P is equal to, this is rho RT. This implies P by rho is equal to RT. Therefore, this is equal to this P by rho, this gamma RT. Therefore, C is equal to gamma RT. Right? So, this simple derivation, this question have been asked several times in examination. Okay. Right. Okay. So, this equation can be written in terms of Mach number also, because Mach number is M is equal to V by C and C is equal to, we know, this square root of gamma RT. That's why V is equal to, this is the velocity of fluid particles, is equal to M into the square root of gamma RT, where M is Mach number, okay, gamma is the 1.404 for air, right? R is the gas constant and temperature. So with the help of this one, the velocity of this V is the velocity of fluid. Okay, right. Next term is called stagnation condition. This is very important. What is the meaning of this stagnation? This is important term. A stagnation condition means, suppose that a fluid particle is expanded in nozzle. If at an exit of nozzle, the velocity of fluid particles is 0, then such condition is called stagnation condition. Dead condition, stagnate, dead. So stagnation condition, as a stagnation condition, velocity of fluid particle at an exit of nozzle will be 0. So velocity of fluid will be 0. This is an important condition. And at this condition, enthalpy of fluid is H naught. H naught. H naught, what is H naught? H naught is stagnation enthalpy. Okay? Right. We know this equation, H plus V is square 2 by constant. This V is the velocity, right? This equation we know. So therefore, suppose that this is entry and exit. This is the nozzle. This is one entry, and this is a stagnation condition. This is denoted by G, right? In this condition, what will happen? If at suppose that at an entry, this enthalpy is H, velocity is V square by 2. This is equal to H naught plus velocity becomes 0. This is 0 by 2, 0 square by 2. This is called stagnation enthalpy. So, stagnation enthalpy is equal to H plus V square by 2. This important equation is very important. Where stagnation temperature at an entry or at an exit of this nozzle, this temperature, stagnation temperature is T naught. The T naught is the stagnation temperature. Well, so overall, this stagnation condition means this velocity of fluid particle will be 0. Whatever fluid is expanded in nozzle, its velocity at an exit of nozzle will be 0, or anywhere, at any condition, not an either only an exit, at any condition when velocity of this fluid particles becomes 0, that means such condition is called a stagnation condition. Okay, so this equation H naught is equal to H naught plus H plus V square to this equation we got. What is H naught? CPT naught. H is equal to CPT, and this is V is the velocity at an entry. Okay, this is velocity at an entry, and this CP by if we divide it by CP, that is T naught. This is stagnation. What is T naught? This is stagnation temperature. Stagnation temperature, this T naught is equal to T plus V square by 2C. And by dividing by T, the T naught by T is equal to 1 plus V square by 2CPT. Okay, we know this CP is equal to, gamma R by gamma minus 1. CP is equal to gamma R by gamma minus 1. So just put the value of this CP in this equation. We will get 1 plus gamma minus 1 by 2 into V square by gamma RT. So, and we know this gamma RT is equal to C square. Okay, so you can write 1 plus gamma minus 1 by 2 V square by C square, and we know that M is equal to V by C. This implies V square by C square is equal to M square. Therefore, this V square C M square. That's for T naught by T. This equation is very important. 1 plus gamma minus 1 by 2 into M square, where M is equal to Mach number. Right? So this is all about the different basic concepts regarding the nozzle. Okay? We have studied the nozzle in brief, and now in this section we'll solve some numerical. Okay? Okay, we'll meet in next section. Thank you very much.